Hello, everyone. I'd like to introduce to you Dr. Ann, who specializes in the studies of X-ray emission from X-ray binary population, both in the local universe and at a cosmologically interesting distances, which are basically greater than 0.1 redshift. She's also the chief scientist for the physics of the Cosmos program. That's NASA's high energy astrophysics and cosmology program. And also she's heavily involved in future missions and as a research scientist at NASA, including co-chairing a science panel for ESA Athena mission due to launch in 2028. Dr. Ann is also heavily involved in future missions, serving as NASA's deputy study scientist for the Laser Interferometer Space Antenna. It's the LISA mission, a space-based gravitational wave mission that's led by the European Space Agency. She also works with the scientists and NASA headquarters on NASA's scientific technical contributions to LISA. Dr. Ann, you can take over now.
Okay. All right. Thank you very much. Ookadook. So I will not be monitoring the chat too closely, but if any technical issues arise, I'll try to glance over there every now and then. Okay. So thank you very much for this opportunity. It's very exciting to be able to go to Africa, even though I'm not able to actually go. It's an honor to be able to speak with you. So today, by the way, I like to put up my photo on the first slide because we're not together in person. We can't see each other's faces, so that'll help you a little bit, maybe to see what my face looks like. Perhaps we will meet in the future at a conference and we'll be able to talk more personally than in Zoom. But I do X-ray astronomy, so very high energy astronomy, and I understand a great deal of this audience are actually radio and perhaps some optical astronomers. So I will be going over a little bit of, how we do X-ray astronomy and what some of the things are that you can learn in the X-ray band, just as a review. This is going to be an interactive talk. So Samuel just put a link up in the chat, and you may want to grab that URL and go ahead and put it in a web browser, because we're going to start off with a very easy question. Oh, and it looks like somebody may have already beat me to the punch. So go ahead and put pollev.com/AnnHornschem074 into a web browser right now. And then please keep it up for the duration of the talk, because what we're going to do is we're going to have these questions as we go through the talk. And okay, great. You can see what's happening as you enter your response. The slide is updating automatically. And this is not a serious question. I'm just sort of curious. By the way, I got up before 7 a.m. this morning, not completely on purpose, but that's what happened. All right, so now this is just kind of to get us going on our response. Okay, so I can see that we haven't quite got everybody who's participating on the Zoom on here. So I'll give people just a second in case you're typing in a URL. You can do this on your phone, but just keep the website up, because as the questions change, it will update on your phone or on your web browser automatically, and you'll get the new questions. Okay, I can see the response numbers rising. Okay, great. Now we're up to almost everyone. And I'm not participating. Okay, we've got almost 100%. Okay, so we can see that we've got a few early risers who got up before 7 a.m., but that the majority of our assembled group here in Zoom got up between 7 and 9 a.m. Okay, so my next question will be more relevant to the talk. Okay, great. We've got now 100% participation on this very important question. We'll now go on to the next question, just to gauge your familiarity with X-ray optics. So how familiar are you with X-ray optics? Do you feel you're expert, or are you more of a, I don't know about it at all? Okay, great. I see the responses coming in. Keep them coming in. And hopefully you noticed, if you just kept the website open, then the question will automatically reload. Okay, so we've got a few people that are somewhat familiar, and then it sounds like it's worth, we'll go through a little bit of a tutorial on X-ray optics so that we will understand how we detect things in the X-ray band. So we'll go ahead and do a tutorial. Okay, thank you very much. Please, if you would, keep that website handy. I'm now going to go and present a few slides, but we will be coming back to questions. I think we've got a total of around 10 questions in this talk. The last one will be, what's your favorite part of the talk? So hopefully there's some takeaway, and it could be answering the questions. I'm not offended if that is the answer, but just keep that in mind. At the end, there'll be an opportunity to just enter something that you liked about the talk. Whatever it is, it could be that the talk is over, whatever it is. Okay. So outline, so a quick primer on, we'll go ahead and do our quick primer on X-ray optics. And then we are going to talk about X-ray emission from galaxies at high energy. So we'll talk about X-ray emission from galaxies and X-ray optics in general, and then what we learn when we look at very high X-ray energies above 10 keV, kilo electron volts. And then I'm going to talk about luminous black holes and neutron stars and nearby starburst galaxies. Time permitting, we will talk about spectral energy distributions of galaxies and the future with a new mission called FORCE that we hope to be launching in around a decade from now. Okay, so first, a quick primer on X-ray emission from galaxies. And I will start with what I really love, which is compact objects, neutron stars and black holes. And so it's fun to talk about how compact objects are. And I like to show this ridiculous picture, which is clearly fake, showing a neutron star hovering over the Canadian city of Vancouver. Okay, but it just gives you an idea of scale. Neutron stars typically have radii that are, we think, in the 10 to 14 kilometer range. So it's comparable to a city that would be the size of, say, Vancouver in Canada. But they contain, they're called compact objects because they have as much mass as the sun, more than the mass of the sun, actually, typically 1.4 up to 2 times the mass of the sun, contained in a ridiculously small region that is only, around 10 to 14 kilometers across. So when we're talking about compact objects, this is the sort of scale to keep in mind. So in the X-ray band, we tend to see these from very far away in external galaxies as accreting binary systems. And so just to orient you, we will have a donor star, and material from the donor star will be gathered in an accretion disk and heated up via friction to very high temperatures as it approaches the black hole or neutron star. And when I say high temperatures, I am talking millions of degrees Kelvin, sometimes tens of millions of degrees Kelvin. So if you can see I think you can see my cursor moving around. So this accretion disk here is extremely hot, emitting X-rays because it is millions of degrees hot. We also have jets that are coming out that are very interesting, but a lot of what I'll be focusing on today are the X-rays that we can see via these accretion disks in external galaxies. And just to remind you, when we look at temperature scales across the electromagnetic spectrum, it's typically, when we're down in the radio, microwave, infrared, we're talking about very cool temperatures that are typically, in the less than 100 degrees Kelvin. When we get up to X-rays, we're talking about 10 million degree sorts of temperatures. And we're also talking about wavelengths that are in the nanometer range. So very short wavelength, very high temperature, very high energy. So we learn a lot from studying accreting black holes and neutron stars. So different types of X-ray binaries, accreting binaries, are indicators of activity in galaxies. So there is a connection to galaxies, bear with me. We're talking about black holes and neutron stars. But the high mass X-ray binaries, which have the high mass stars as donors, are like the smoking gun that goes off when the stars form, because you only have these very massive stars when star formation regions are very young. So high mass X-ray binaries correspond to recent vigorous star formation. Whereas the low mass binaries, it takes a much longer time for a low mass star to evolve to a Roche lobe overflow phase. So these are indicative of past star formation and are really a bit like archaeology, where we can look back in time at a galaxy and learn about a galaxy. So this is what we do. We study these X-ray binary systems to learn about the galaxies in which they live. So when we're talking about normal galaxies, which is what I'm talking about, and I think many of you study galaxies, but I'll have a question about that later, actually, to ask you about what you study. But I'd like to talk about the Milky Way Galaxy. And this is a slightly complicated figure, but basically this is the center of the galaxy, and this is from Kretschmar et al. 2019. It's a map using the integral satellite. And all the blue circles are OB star associations, okay? And then if you look at all these red points, those are high mass X-ray binaries. And this right here, this symbol, hopefully you can see my cursor, there's a little asterisk. That's our location at the sun, the location of the sun, okay? So these are all the spiral arms that, that we know about in our galaxy. And you can see all these red high mass X-ray binaries that are peppered around the galaxy. And you might notice there's a whole bunch clustered down here. Well, those just happen to be ones that we don't know the distance. So they've been placed on the plot just at a rather arbitrary distance, the distance to the galactic center. But what we can start to notice, and there have been studies, is that we find statistically that there's more of these high mass X-ray binaries corresponding with OB stellar associations. So they are associated with star formation. And our Milky Way galaxy, by the way, is a very good example of a normal galaxy whose X-ray emission is dominated by these binaries, also by hot gas, which I will talk about only briefly, but it is not dominated. This center of our galaxy is, I like to say, a pathetic excuse for a supermassive black hole. We have a supermassive black hole, but is not active. So our galaxy is very much dominated by the X-ray binaries and by the hot gas. For reference, since I'll be mentioning luminosities a bit later, the luminosity of our galaxy in the X-ray band, 0.5 to 8 keV, is 6 × 10 to the 39 ergs per second. That's just a good reference number to keep in mind as we go forward. But if we look at a distant galaxy that is a lot like the Milky Way, this is actually what we might see. This is a Hubble image of a galaxy. And we used the Chandra X-ray Observatory to detect an X-ray source. And this is very typical because X-ray sources are variable. And at any one time, there might only be a single bright binary that dominates the X-ray emission of an entire galaxy. This is quite typical when we look at distant galaxies, that we might see just a one point source, maybe a handful of point sources, very luminous point sources that are dominating the X-ray emission. So this X-ray source dominates the X-ray emission of this distant galaxy. Okay, so just continuing our orientation here. So why we would study X-ray emission from galaxies? We can get at star formation in heavily obscured areas, just like if you go to the doctor's office for an X-ray and the X-rays go through the flesh of your body, so you can see the bone. The X-rays also go through obscuring dust to get to heavily obscured areas in galaxies. The accreting binaries give us an independent probe of star formation, the initial mass function, and the emission can persist for a very long time, giga-years after the star formation has happened. And the supernova and winds enrich and add metals to the interstellar medium and the intergalactic medium, affecting star formation and evolution. I'm not going to talk about the diffuse gas as much, but this galaxy is M83. It's a Chandra image. And you can see all the point sources, these little points, are all these X-ray binaries. This is a relatively nearby galaxy where you can detect a whole bunch of X-ray binaries. But you can see this beautiful image of the diffuse hot interstellar medium. This is a very important topic, but I am focusing today on the X-ray binaries, the black holes, and the neutron stars. Okay. So a quick primer on X-ray optics and why we study galaxies at very high energies. So I'm just looking at the chat, and I'm hoping, Eric, are we still good? Sound still okay?
All is good.
Okay, good. Thank you. I just want to check occasionally and make sure that we're still connected. Okay, a quick primer on X-ray optics and why we study galaxies at high energy. So this is what X-ray optics look like. And this is where it would be so much better if I was able to actually stand in front of you. So hopefully you can see the little image I have here. But basically, you can think of the conic section. If you're able to see my image, you can kind of see my hands. So think of a parabola, but when you're dealing with optical light, the optical light comes down to the bottom, to the base, and gets reflected. With X-rays, we're dealing with the outsides of the conic section, okay? So you can kind of think of our X-ray optics like they are light buckets with holes in the bottom, and the X-rays reflect at grazing incidence, very shallow angles, kind of like skipping a flat rock over the surface of the water. Hopefully you've had the experience of skipping stones before, but something that skips over the surface of the water. Grazing incidence is like the X-rays are reflected at tiny angles using paraboloids and hyperboloids, the same kind of conic sections that we use for all of our optics, and then focuses the X-rays down at a point. So what we do is we nest together many of these shells, because as you're looking down the shell, and again, if you can see my image, you can look at the picture of me right now. If you're looking down the shell, the cross section is actually tiny. The collecting area is tiny. So we build up many shells to increase the cross section collecting area of the X-ray optics. So this is actually what we've done for the NuSTAR mission, but this is a technique, what I'm showing here, that we have used for quite some time now, 30 plus years in the X-rays for lower energy X-rays, but is relatively new for energies above 10 kiloelectron volts. In the past, there have been hard X-ray missions that operate at very high energies, but they use a different strategy called coated masks, where they punch out a metal plate and put a pattern in, and then they use that pattern to tell where on the sky the X-ray emission is coming from. This works fairly well, but it only allows us to locate things to degrees, many tens of arc minutes, maybe tens of arc minutes. But overall, it is not very effective for focusing X-ray light. Whereas NuSTAR, which is a relatively new, actually, it's 9 years old now, so I guess maybe I shouldn't say that anymore, but it seems new to me. 9 years old, Explorer mission was the first ever mission to use grazing incidence optics, like I just showed you for Chandra, in the harder X-ray band. So again, we send the light at these very grazing incidence angles, but actually focus it. And this technology allows us to get down to arc second type of resolution, except NuSTAR doesn't have arc second resolution. So by the way, this is something that'll come up later in a question. So I'm just going to give you the answer right now. You may know about the Hubble Space Telescope that has sub-arc second angular resolution, and Chandra X-ray Observatory has arc second level resolution. NuSTAR is much more modest. It's about an arc minute angular resolution, and the center of the PSF is about 20 arc seconds. So the imaging quality is nowhere near as good as Hubble, but it is the best we've ever had in the hard X-rays. So my colleague at NASA Goddard, who I have not seen in person in quite some time due to this pandemic, but his office is right next to mine, Will Zhang, helped produce a large number of glass elements for the NuSTAR X-ray mission, 3,000 pieces of glass for NuSTAR. And this is what the NuSTAR optic looked like. So now you can see that we've got the primary and the secondary hyperboloid and paraboloid section, and we've got a whole bunch of stacked sections 3,000 pieces of glass total. So the X-rays can come down and encounter a whole bunch of glass and be focused at the focal plane. And once we build up an optic like this, this is what we get. So this is collecting area in centimeter squares. And again, this is very modest. If you're a radio astronomer, you're probably laughing at me right now because our tiny collecting areas are in the hundreds, maybe up to 1,000 square centimeters. But you know, X-rays, it's very hard to build up a lot of collecting area. And this is a function of energy. Now, from 5 to 80 keV, high energy X-rays. By the way, this would be in the dentist office. Typically, the X-rays would be above 10 keV. So Chandra and XMM Newton are the flagship observatories for NASA and ESA. Chandra has a half arcsecond PSF. XMM Newton has a 15 arcsecond PSF. And you can see there's a little bit of a trade-off. Chandra has an exquisite vision and angular resolution, but not as much collecting area. XMM Newton compromises a little bit on the PSF, but has much better collecting area. NuSTAR doesn't have as good of a PSF, but extends up to very high energies. Okay, so now I'm going to ask a question, and part of it is to see how I am doing. So the question, so hopefully you've still got the URL up from the last time. So my understanding of X-ray optics improved in the last few minutes. Don't be shy. You can send me some suggestions for improvement, if not, but I'll give you a second to answer the question. Okay. All right, it looks like we've already gotten a fair number of responses. Okay, so it looks like I did an okay job, and we'll continue with the talk. All right, so next one is more of a question to test for comprehension. Oh, I can see a couple more responses came in. Thank you very much. All right, so the next question is, which statement about X-ray optics is true? All right, so check among the answers. Okay, good. Well, sorry, I'm maybe giving things away already, but I'll let you study them. And I definitely hope that A was definitely a test, because I think I gave that one away to you, that I told you we are not the same as Hubble. Okay. I was saying, whoever answered A, we have not achieved imaging quality comparable to Hubble. We're not there yet. Okay, I'm giving you a second. All right, it looks like we already have quite a few responses. Okay, great. So yes, the answer is B. X-rays must be reflected at very shallow angles along the sides of concentric shells. Okay, and all the other statements are false. So we'll continue on. Now, why study galaxies in the very hard band? So again, I'm very interested, and my research group is interested in neutron star and black hole demographics. So we can actually learn about, to get into more details, supernova explosion mechanisms. It's very difficult to model supernova explosions, but if we know about the population of neutron star and black holes left over, it's actually a constraint to those models. We learn about the final stage of stellar evolution, like the strength of winds. If winds are very strong and take a lot of matter away, then the resulting compact object will be much lower mass. You might expect to get, for instance, fewer black holes. And we can also learn about the initial mass function by the distribution of properties of black holes and neutron stars. Another very interesting topic that we can learn in the hard X-rays is about particle acceleration in starburst environments, because supernova explosions accelerate particles. And since I'm talking to some radio experts who assuredly must study synchrotron radiation in the radio band, this is actually something where hard X-rays and radio intersect. Again, I'm focusing on compact objects, but for a future talk, I have a colleague, Dr. Tony Venters, that you might want to have speak about that particular topic, which I think you would be interested in. So now we're going to get into a little bit of details about accretion states in galactic hole binaries. So this is some of the more detailed material that I'll be going through in this talk. So thanks to a mission that operated for a long time called the Rossi X-ray Timing Explorer, which I show up here, we have decades of data monitoring the state of black holes. And we find that black holes actually go through a series of transitions where, for instance, they'll be in an ultra soft state where the accretion disk is very full, and then there is a low state where the accretion rate is lower and the accretion disk does not come in as far, and we have more non-thermal emission. And there's all kinds of states in between. So it's basically black holes go through a variety of accretion states, and their spectra change based on which accretion state they are in. So here I show the spectra, and I know this is an X-ray spectrum, you won't be quite as familiar, but the main thing is to look at the shapes of the spectrum. So this is actually going from below a kilo electron volt up to very high energies, 1,000 keV. So that's more like an MeV. So when you look at the X-ray spectra, you can see that there are very big differences. So the interesting thing, if we look in the Chandra bandpass, which is a wonderful observatory that operates in the 0.5 to 8 keV band, the trick is if we look at an extragalactic population where we only have colors, X-ray colors or spectra, it's very hard to tell the difference between these different states just looking in the Chandra bandpass. Whereas if we look at higher energies, there's a much more dramatic difference in the spectra for these black holes at higher energies. And this is a tool then that we can use to figure out what we're looking at in external galaxies. Okay, so I'm going to explain this in a very basic level, but I'll show you what it looks like in data. So we can use data on a few dozen extremely well-studied black holes and pulsars and neutron stars to create color diagrams or color magnitude diagrams that would be somewhat similar to what you have in the optical band. But here, these are X-ray bands that we have constructed to allow us to tell the different colors of X-ray sources in the NuSTAR bandpass. So what you can see is that we can differentiate soft, intermediate, and hard state black holes into very different parts of the diagram. We can also study accreting pulsar systems. So these are very high magnetic field neutron stars, and they occupy a distinct part of color space. And just in case there's a question coming up, let me say that again. Pulsars are in a very distinct part of hard X-ray color space, because that might be relevant in a minute or two. Okay, so this is then if we make a color plot, that was a magnitude color plot. So here we've now got the harder band, 12 to 25 keV. We can see that things further, this is actually the best diagnostic diagram, because the black holes, which are the red, green, and blue, really separate from the neutron stars, which are down here in cyan, the low magnetic field neutron stars, and the accreting pulsars, which are up here in magenta. So we have these distinctive parts of color space. So the fun thing we can do is that we can look at external galaxies and see where the X-ray binaries are on these sorts of diagrams. But next, we're going to have one quick question. And I hope I covered everything in the question, so this will be a test for me. Okay, so which statement about black holes is false? So I'll just go ahead and read these. Stellar origin black holes may undergo a state transition during which the relative intensity of the accretion disk and corona change. Pulsars occupy, so we're picking which one is false. Okay, so pulsars occupy a distinct region of hard X-ray color space. The X-ray colors of black hole binaries are identical at low energies and high energies below 10 keV and above 10 keV. And the X-ray colors of pulsars are distinctive from those of lower magnetic field neutron stars, none of the above. So pick what you think is incorrect, the false statement. All right, and I'm checking. I've got an iPad here so I can see how many people have responded. Okay, so we're already up to a decent fraction of people have responded. Okay. Okay, yeah, we've got just about everybody now. Okay, so C is the correct answer. The X-ray colors of black hole binaries are actually very different at low energies and high energies. So just to check, because we did get some response for A. So that's actually true. So black holes may undergo a state transition during which the relative intensity of the accretion disk and corona change. So just to go back, this diagram that I show here, I maybe didn't do a good enough job explaining this, but this is the corona in here. The blue is the non-thermal emission particles that are very hot in the center near the compact object. And this is the accretion disk. So we do find that the relative intensity of the accretion disk and the corona does change in black holes. Okay, but it's good that we had a chance to go back and review that. Okay, so now we're going to talk about luminous black holes and pulsars in nearby starburst galaxies and place them on these diagnostic diagrams. So these are the names of some of my collaborators, and I show here some of the galaxies to give you some idea that we study relatively nearby galaxies. As I mentioned, NuSTAR is great, but the PSF is about an arc minute with a 20 arc second core. So since it's not as good as Hubble, we really do have to confine ourselves to relatively nearby galaxies that are within a few megaparsecs. So this is one of the galaxies that we've studied, M31, the Andromeda Galaxy. And we've had a number of papers on results in this galaxy. So I encourage you to look up some of these papers by Tom Macarone, Mihoko Yukita, Margaret Lazzarini, Nevin Vulik. I'll be telling you about a paper that's in preparation by Dan Wick. So NuSTAR only has an 11 arc minute field of view. So we picked a region in Andromeda and we studied it to very deep, in deep exposures. This source right here, by the way, is the subject of Mihoko's paper. It's a very blue source, but I'm going to take you through what we found when we studied these various point sources. So every point that you see in this image is an X-ray source that is an X-ray binary, okay? So I'm going to tell you about these X-ray binaries. And just to orient you, the color in this X-ray image is color-coded by the energy of the X-ray. So if it's blue, it's emitting at very high energies, 12 to 25 keV. So just to advertise some of my collaborators' work, which I won't cover as much, but Tom Macarone wrote a nice paper about the globular cluster sources, the bright globular cluster sources. And my colleague, Mihoko Yukita, who is flying to Japan today, please send positive vibes to her. She wrote a nice paper on this very hard X-ray source, which we think is a pulsar. But I'm going to tell you about the general population of X-ray point sources. So hopefully this looks familiar to you because I showed you a version of this earlier. And to be completely honest, I must show you what our typical error bars are. This is a modest X-ray mission, the first time we've ever flown a hard X-ray mission. So our errors are a bit big. However, we can show you that most of the point sources are consistent with being neutron stars. And there might be a question coming up later. So let me say that again, that most of the point sources, the X-ray binaries that we detect in M31 Andromeda are neutron stars. We do think we have a few sources that are consistent with black holes, but you can see we have pulsars and a large number of low magnetic field neutron stars. And this is a statistical result. It's a little bit hard to say for any individual source what you have, but statistically that appears to be the case. And then when we look, again, this is the optical image, or perhaps UV image in the background. And then we have, you can see the blue, the cyan, and the hot pink magenta are the neutron stars, the pulsars, and the low magnetic field neutron stars. And one interesting suggestive result, if you look at the magenta sources, the pulsars, you can see that they actually very well follow the spiral arms of the galaxy. And that's what you expect. You expect young pulsars in high mass X-ray binary systems to follow the spiral arms, or you expect to see more star formation. Okay, so I've got one more question coming up just to check, and hopefully I set you up for this one. So which statement is true concerning black holes and neutron stars in the NuSTAR M31 study? More neutron stars were found than black holes. More black holes were found than neutron stars. The number of black holes and neutron stars are about the same, or none of the above. Okay. It looks like we have very quick, good response here. Okay, right. There were more neutron stars found than black holes. But then let's see what happens when we broaden the study to a much bigger sample of galaxies. So don't worry too much about this plot, but these are all the galaxies that were included in Vulich et al. 2018. Nevin Vulich wrote a paper. And the main takeaway here is we looked at a variety of galaxies that had a range of star formation rate and a range of stellar mass. Here's our Milky Way, this little X right here. So the galaxies that are close to the X are more like the Milky Way in terms of star formation rate and stellar mass. You can see that we had some dwarf galaxies down here at lower mass, but these lines show specific star formation rate. We divide star formation rate by stellar mass, so they're more star bursty if they're higher in that parameter. So we have a range of galaxy properties. So this is what happens, and I realize that this plot is a bit messy, but this is the biggest analysis that we've done to date of X-ray point sources in external galaxies. So we've got 128 individual detected X-ray binaries. And interestingly, if you count up everything that we've got here, we find a similar number of black holes and neutron stars compared to Andromeda. Now, here we're looking at a much more luminous population because these galaxies are farther away and our sensitivity isn't as great. So there's certainly a selection effect by looking at very luminous sources. But we do find of these 128 sources that we studied in Vulich et al., that about half of them are black holes and half are neutron stars. We can also start to look at the properties of neutron stars and black holes. And this is the black hole fraction. So as a function of luminosity, going from 10 to the 37 to 10 to the 41. And by the way, for reference, at the beginning of the talk, I told you that our entire galaxy, Milky Way, is about 6 times 10 to the 39 ergs per second. So we actually detected some individual point sources that were more luminous than our galaxy, just for perspective, okay? But as you go up in luminosity, so you notice at higher luminosities, it's much more likely that sources are black holes. So the black hole fraction goes up at higher luminosities. This is not a huge surprise because for various reasons, we do expect black holes to be at higher luminosity. Interestingly, this dip right here is suggestive that there might be basically more neutron stars. So if the black hole fraction goes down, that means the number of neutron stars has gone up. And it seems to be that right around the Eddington limit for neutron stars, you find a bunch of neutron stars. Our error bars are so huge, I would not bet my life on this, but it's an interesting thing to investigate in the future if perhaps neutron stars like to cluster near their Eddington limit. Okay, so I'm going to ask you a question now that is really about you and not about this talk. So, and then, okay, I see that there's some questions coming in, but it looks like questions I can handle at the end. Okay, so I'm curious about you and your research, your interests. So my research concerns objects. So this one, just tell me about you. So, all right, nearby universe that are in the local group. And apologies if, I mean, if you're an exoplanet person, then that's within the galaxy. This is a little bit biased towards extragalactic astronomy and galaxies. Okay. All right, so I'm gonna look at the responses. All right, so it looks like we're up to a decent fraction. Oh, okay, great. Give people a chance. Okay, it looks like a few people. Okay, so we've got somebody that does very high redshift studies beyond reionization. Okay, good. I was expecting a few more responses. It looks like we just got a few more. Okay. All right, so this is always very interesting to me when I give a talk. So it looks like actually the majority of the group that we have here on our Zoom meeting today, the majority studies galaxies at intermediate redshifts, 0.02 to 3. But then we've got a decent, the second runner-up is the relatively nearby universe. That's actually what I'm talking about right now. But interestingly, looks like we haven't got anybody that really studies local group galaxies. Okay, so this is very interesting. All right, thank you very much. It looks like, just looking at the responses, that we've got a significant fraction of our audience. It looks like somebody just changed their response. This can be hard. If you study more than one thing, just pick whichever one you feel like is most representative. Okay. All right. Well, this is interesting. I think it's always interesting to learn about the audience. As I go through the next section, we're actually going to be talking a little bit about the higher redshift universe and how some of our local galaxy work can cause us to understand better the high redshift universe. Okay, but it looks like we're an intermediate redshift, relatively nearby universe crowd with a few other people doing other types of things. Okay, so understanding black hole and neutron star populations through X-ray SEDs of galaxies. So this is VV114, a very low metallicity starburst galaxy that's studied by another person in our group at NASA Goddard, Kristen Garofoli. And just for scale, I want to point out immediately that this is 10 arc seconds, this line right here. And this is actually an adaptively smooth Chandra image. And the reason I'm pointing out those things is because NuSTAR cannot possibly spatially resolve this galaxy. Okay, so you can see here 4 to 25 keV NuSTAR intensity contours. So it's basically one big point source to NuSTAR. But this galaxy has been well studied at a variety of wavelengths, and we can still learn a lot about starburst galaxies by studying their spectral energy distributions. And this has great implications for our understanding of the very early universe. Okay. So Kristen Garofoli has a very nice paper, which I encourage you to go check out because I'm going to be giving a very quick overview of it. And in it, she models the Xray emission, and this is nu spectra being shown here from very low X-ray energies well below 1 keV up to about 20 keV. And what the models predict, by the way, is that at lower metallicity, so this is 0.1 solar, at lower metallicity, it is predicted that, for instance, stellar winds will be very weak in stars. And the result is that more massive compact objects will be left behind. And when we have more massive compact objects and more compact objects, this boosts the overall X-ray emission. So at higher energies, what you see here, this is basically a power law that is indicative of what we expect for very luminous accreting binary systems. Down at lower energies, and again, I won't be discussing this too much, but these are models of the hot gas emission in these galaxies. And there's some variation for metallicity down here, but the whole thing scales with metallicity in an anti-metallicity sense. The lower the metallicity, the higher the X-ray emission that is expected. And then when we actually fit data for galaxies for which we have well-measured metallicity, we find that this actually does bear out. So these first 3 galaxies are all around solar metallicity. And if you sort of squint, you can see that they're coarsely consistent with that first model. And then we put VV114 on the plot at half solar metallicity, and it's much higher than those solar metallicity galaxies. And then if you find a very low metallicity galaxy like NGC 3310, which is at 0.3 solar metallicity, it's got an even higher amount of X-ray luminosity. And this is all very interesting and very important to understand. I'm not actually going to go through the variations because I want to be respectful of your time. But this is why it's so interesting, because at early times in our universe, and now I'm talking about very high redshifts, we have now learned that X-ray binaries can be important for heating the intergalactic medium. And now I'm talking about the primordial intergalactic medium in the very early universe. And so this is, if we plot the X-ray emission from X-ray binaries from galaxies over cosmic time, this is work by a colleague, Brett Lemur et al. And he's actually studied high redshift galaxies, X-ray binaries from high redshift galaxies, and shown that this is how it evolves. And also we've done some modeling out to high redshift. If we compare this with the X-ray emission from supermassive black holes, it turns over much more quickly at high redshift. So the interesting thing then, as we get up to cosmic dawn at redshift 10 to 20, it is actually X-ray binaries that in galaxies that are producing a decent amount of X-ray emission and might be the important sources for heating the primordial intergalactic medium. And there's actually been a number of interesting experiments proposed in the radio band to study the primordial intergalactic medium. This is again where X-rays and radio astronomy intersects, because the X-rays are important for heating the intergalactic medium, but in the radio band, you can actually measure the properties of that primordial hydrogen directly. Okay, so we're almost to the end of the talk. And so I am finishing up, Eric, don't worry. So one more question here. When we observe galaxies with NuSTAR at high energies, which statement is false? This is actually a couple different slides combined together. So the more luminous the point source, the more likely there are black holes. We're picking something false. Higher metallicity, higher X-ray luminosity. Lower metallicity, higher X-ray luminosity. And then this one's a little bit silly because it's so specific. In a sample of 12 galaxies, 128 neutron stars and black holes were detected. None of the above. So I'll give you a chance to finish that one. And then we'll have a very brief description of future missions and we'll go on. Okay. All right, I'm going to go ahead and tell you, you were right. Good job. The higher the metallicity of the galaxy, the higher the X-ray luminosity. That is false. Lower metallicity galaxies actually have higher X-ray luminosity. So great job, group. All right. So now I'm totally switching topics here. So what would be your guess at the cost of the NuSTAR Observatory, which is a small Explorer mission, not including the launch vehicle? And this is a bit of a silly question, so don't worry about the answer. But just if you had to guess how much a mission like this costs. And you don't have to pay for the rocket, you're just paying for the satellite with the optics and the detectors and all the stuff on the satellite, but you don't have to pay for the launch vehicle. All right. Okay. Giving people a chance. Okay. So, and again, don't worry about this one because there's not necessarily any reason you should have known this. Okay. So the correct answer is actually, it's just over $100 million, just for reference. And that's a lot of money However, compared to like the Chandra X-ray Observatory or the XMM Newton X-ray Observatory, those are billion-dollar class missions. So this is actually one of the smaller categories, not the smallest, but one of the smaller categories. So it's actually around $120 million is what we paid for NuSTAR. So we are actually collaborating with some colleagues in Japan to look at a future mission called FORCE. It is focusing on relativistic universe and cosmic evolution. And if you're wondering why there is such a contrived acronym, Koji Mori and myself, we love Star Wars. So yes, this really is a bit about Star Wars. We really love Star Wars. So we came up with an acronym that allows us to connect it back to Star Wars. So, but it's looking at the non-thermal universe and cosmic evolution of sources. So it's a broadband X-ray imaging spectroscopy mission from 1 to 79 keV, and it's going to have much better angular resolution, better than 15 arc seconds, because we had an arc minute before, remember? So, and again, I'm going to step through this a little bit fast because I know that we're pretty much out of time, but it will have 2 identical mirrors. The detector will be made in Japan, and the optics are going to be made at NASA Goddard Space Flight Center. So you can see the little image showing the optics up here at this end. This is the optics, and then the detectors down at the other end. I need to show you that there's a big team of lots of people, lots of Japanese people, and then a small number of us who are from NASA Goddard. However, in traditional fashion, this mission will be open up to the world community for proposals. And we hope that it would be launching maybe around the year 2030. So the scientific goals are to complete a census of black holes across the range from highly obscured supermassive black holes. We want to find the buried ones that are very hard to find in other wavelengths, all the way down to the stellar origin ones that I was talking about. And we're also going to look at particle acceleration in the universe, in supernova remnants and in clusters of galaxies. And again, I would encourage you to maybe invite Tony Venters in the future to talk about particle acceleration, because I know that this might be of interest to many of you who do radio astronomy. Okay, and we'll also be studying supernova explosions to understand nucleosynthesis in supernova. I just want to show you, I'll leave you before we get to the very end of the talk with what an observation of NGC 253, which is a starburst galaxy we studied with NuSTAR. This is what it looked like with NuSTAR on the left, 495 kiloseconds with NuSTAR. We detected only 30 point sources. With FORCE, we can study this galaxy for only 150 kiloseconds, and we will detect so many more point sources and we will not be so confused. Our error bars will be wonderful, and a lot of the science I told you about will be much easier to do. So may the force be with you. And then my next question is both a bit silly, but also somewhat serious. So I also want to get to know my audience a little bit. Please choose the best response from the choices below. And I'm not going to read these out loud. I will let you read them and decide which one best represents you. All right. And don't worry, I'm not offended if you are not a Star Wars person. That's okay. And yes, I appreciate your honesty, because I like to know my audience. I will warn you that the next question will be about your favorite part of the talk. Okay, I'll give people a chance, and some of you might be torn trying to decide how to answer this question, so I apologize. I realize this is a serious topic, trying to decide about Star Wars, Star Trek, and other things. All right, so just checking our responses. We've still got a couple coming in. All right. Okay. All right. So Well, it looks like we've got a decent number of Star Wars fans, but you know, we have also some Star Trek and people who think there might be more to the universe. Okay, all right. So it's always interesting to see where our particular audience stands on very important topics. All right, I'm being a little tongue-in-cheek. I know there are much more important things than Star Wars, I think. All right, so at this point, this will be a slightly different version of the question. So it asks you to type in what your favorite part of the talk is. And I believe you will also be given the option if you want to vote up somebody else's option. So go ahead and start typing, and feel free to say that you're glad the talk's over. Maybe try to come up with a kind way to say it, but whatever it is, go ahead. So we'll give you a minute to type. Okay, Xray Optics. Okay, great. And you can see there's a number next to it. So if you want to, instead of typing in your own thing, you can vote for something that somebody else entered in. It seems to be we're getting a lot of votes for Xray Optics. Okay, I'm actually glad to see this. All right. All right. And I'm just gonna check and see how many. Okay. So it looks like people are still typing. This one takes a few more minutes. And I apologize because there's so many of us. Not everything may display here on the screen. So it'll show us our top votes. So you can go ahead and vote on your favorite parts. Okay. Okay, good. So it looks like a few people are still responding. So I'll give you a couple more minutes. Okay, looks like I can scroll down. I'm gonna have to go look at this one to figure out what the favorite part is. Okay. Oh, I love it. The Q&A sessions, and of course, Star Wars. Okay. 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 Okay, so this one was, I figured out how to click learning more about Xray optics. Okay, great. Okie doke. Okay, so it looks like I did an okay job on the Xray optics. I'm glad to hear that. And I really hope it's easier to explain these things when we're together in person. So maybe we'll have an opportunity in the future. I certainly hope to have such an opportunity. Okay. Oh, my mind is overflowing with puns. Okay, I love that. Thank you very much. That's very important. Okay, I think we'll go ahead and move on. But I want to thank you for taking the time to type some things. And I actually take this very seriously and try to improve talks based on feedback from the audience. Okay, so very short and sweet finale here with NuSTAR, a low-cost explorer mission. We've been able to separate neutron stars from black holes and determine well the overall X-ray SED of galaxies. A follow-on to NuSTAR could be a mission like the Japanese concept FORCE at low or moderate cost. This is my email address, and this is my group website. I will admit to you that I'm a little terrible about email, but I will eventually respond. You might have to try more than once. We're in the crazy, we're having a crazy summer in my household right now with my daughter being home, so just bear with me. Anyway, it was a pleasure to speak with you today, and you were a great audience. I want to say that it doesn't make up for not seeing your faces. I wish I could see your faces, but it does make me feel a little bit like we're connected during the talk. So my most sincere thanks to you for being such a good participant in the talk today. All right, thank you very much, and I will turn the floor over to Eric.
All right. Okay. Okay, thank you, Dr. Ann. And now we have a question here. It's on slide 21. Is there a correlation between gigahertz packed AGN and these LHS emissions on slide 21?
Slide 21. Okay, I'll just go back to slide 21. Give me a second. The computer. We're getting there. Don't worry, we won't have to scroll through absolutely everything. Okay, almost got it up on the screen. Okay, slide 20. Oh, that's 2021. Okay, this one. Okay, and then is the question in the chat window?
Yes.
Or...
yes.
Okay.
Yeah.
Okay. All right. And I'm sorry, maybe I can't see it. Can you go ahead and ask again?
Okay, so the question is there a correlation between gigahertz peaked AGNs and these LHS emissions, that is with the significant structure or evolution in spectra?
Okay, it's an interesting question about the connection between AGN and these black hole binaries. So just by the way, AGN do exhibit some similar state transitions to black holes, and I encourage you, there's some lectures out there by Chris Doan. She's the author of this particular summary paper. She recently gave a very nice talk on AGN state transitions for a workshop, an Athena Rubin synergy workshop that we just had a couple months ago. So I believe that lecture is publicly available. That's actually exactly on this topic on supermassive black hole state transitions. So that's my way of saying, so I don't study the supermassive black holes, the AGN, nearly as much. But I will tell you that there is a you actually do expect that you get more emission coming out from the poles, and there is a correlation in the radio that we have the radio jets peaking when we're in the lower states, and not as much when we're in the higher accretion states. So there is a correlation, anti-correlation, depending on how you look at it, with the radio emission and X-rays. But I'm less familiar with exactly the
next question, which asks on slide 2021, where you discussed the accretion states of galactic black hole binaries. Is there a chronological order for these accretion states? And what are the timescales for these accretion states?
Okay, that's a really great question. I see Clinton Stevens asked that question. It's a very good question, and the answer is quite actually complicated. Let me see if I can. Okay, so this diagram is probably a decent one. So yes, we typically will see a pattern where sources start out in a low hard state and then move up and then sort of come over. The time scales actually vary a little bit, but we're talking transitions can happen very quickly on the order of days. So we have The Swift Observatory often alerts us when something suddenly, an X-ray binary transitions to a high state, but sources can remain in the high state for weeks, months, in some cases, years. It really depends on the geometry of the particular binary system. And you can imagine, how full the accretion disk gets, what the separation is between the primary and secondary star. So it does vary a bit, the timescales. And there have been some interesting studies on by an author named Tetarenko on the papers on failed transitions. So not all compact objects, even though quite a few do go through these very regular states, we find that there are some lower mass, lower accretion state sources that sort of never manage to go through these accretion states. So there's still quite a bit that we're trying to understand. There is, by the way, a bit of a hysteresis effect where some sources come back through the bottom part of the diagram, and there's actually a little bit of there can be ambiguity if you're not tracking the source about exactly where you are in the diagram. So the important thing when studying these state transitions is to monitor a source daily with as many different techniques as you have to sort of track the source going through. So it can be very difficult, and this is what we're working on with NuSTAR, but it's a little tricky to tell just with an individual observation exactly where a source is in the diagram. The best way, of course, is to track the source through its phase transitions, but that's what we're working on calibrating. Okay, hopefully I answered Clinton's question.
Claim 3 sigma detections and all of that. So will the upcoming missions fix all these issues? Will you be able to say if there's like multi-phase structure within these hot turbulent coronal medium?
Let's see. So yeah, we haven't had very much. Let's see. So with respect to signal and noise, there's actually a couple problems. One, the mirrors that we've flown to date don't collect as much light as we would like to give us a signal noise. Well, we measure our spectral resolution in electron volts, so it's a couple EV, so resolving power of thousands at the higher energies in the Athena band. But you're going to be able to study the hot intercluster medium and compact groups. You'll be able to study the hot intergroup medium and intercluster medium to determine things like the role of turbulence and other physical effects in the hot gas. And of course, there's been a very interesting paper that came out of the Hitomi mission a few years ago on the state of the intercluster medium and Perseus, studying the turbulence there. So that's going to be a huge topic. So encourage you. So there's going to be a lot that we're going to be able to do to learn about the state of the hot gas in clusters and compact groups, which we think is the dominant mass component in those structures. So we're going to learn a lot about the formation of clusters and compact galaxy groups. But in the meantime, while we're waiting for Athena XIFU, there is the XRISM mission, which is XRISM, is going to be launching in late 22, possibly early 2023. It's a Japanese NASA mission, which also has a calorimeter on board. It will be very good. Athena XIFU will be much better, but we will have this opportunity to get calorimeter high resolution X-ray spectra. And by the way, it's true imaging spectroscopy, where every pixel in the camera is a spectrometer. So be able to get spatially resolved, non-dispersive X-ray spectroscopy of the intracluster medium in a variety of clusters with the XRISM resolve instrument, and then later with the Athena XIFU instrument. But again, this will be high resolution X-ray spectroscopy, where we're going to be able to resolve, for instance, the helium-like triplet in a variety of lines to do precision density and temperature diagnostics, and also to look for signatures of turbulence in the intercluster medium. So it'll be very detailed diagnostics of the state of the hot gas in these structures.
Hi, so a couple of follow-up questions. So my understanding with X-ray spectroscopy is that we have not been able to achieve sufficient SNR to claim 3 sigma detections and all of that. So will the upcoming missions fix all these issues? Will we be able to say if there's like multi-phase structure within these hot turbulent coronal medium?
Let's see. So yeah, we haven't had very much. Let's see. So with respect to signal and noise, there's actually a couple problems. One, the mirrors that we've flown to date don't collect as much light as we would like to give us a signal noise. But it's also, so we've been able to do very good spectroscopy using dispersive elements like gratings. So we've done very good high resolution X-ray spectroscopy, but there's a limitation in the technology. So collecting area, as you point out, is a huge thing. We need a bigger mirror, absolutely. But there's this corollary problem. Like if you want to study a cluster of galaxies, it's a big diffuse object on the sky. And our X-ray gratings are really well suited for point sources because they disperse the light into a spectrum. And unfortunately, if you have a big extended object, the light gets basically smeared by the extent of the object. But if you use instead a different kind of technology, the calorimeter doesn't disperse the light. It just measures a spectrum at each spatial location. Each pixel in the calorimeter is a spectrometer. So this different technological approach allows us to get a high resolution spectrum at every location. And here the problem, one of the big problems, is we just simply haven't flown an X-ray calorimeter in space for very long. We've had sounding rockets, and I'm sure some that you know about the tragedy of the Hitomi mission that was lost. Unfortunately, the entire mission was lost after a few weeks of operation. So they just didn't get the chance to observe very many sources. So the XRISM mission will have modest spatial resolution, will have excellent spectral resolution and good collecting area. So I think we're going to see quite a few breakthroughs with the XRISM mission. And by the way, Shriram, if you're interested in this, I have people in my lab that could give a talk specifically about science with X-ray calorimeters, focusing on clusters. Please reach out because I'd be happy to help arrange for a future talk that's aligned with your interests.
Thanks. I'll send you a mail. Thank you so much.
Okay.
It's really interesting to learn about this.
Yeah, great. Glad to talk with you.
Okay. Thank you so much, Dr. Ann, for the very informative talk. We really enjoyed it.
Thanks, everybody. Really appreciate it.
All right.